Hi everyone, it's Dr. Major. I'm going to be talking with you today about when we compute our independent samples t-test. Now remember we said another name for our independent samples t-test is the pooled variance t-test. So let's start by talking about when we should compute it, and then we'll get into how we compute the pooled variances or independent samples t-test. So we compute this test when we want to test hypotheses concerning the difference between two population means where the population variance for both populations is unknown, or if we don't know the population standard deviation for both groups. But if we don't know variance, then we don't know standard deviation. If we don't know standard deviation, then we don't know variance. Essentially, another way to say this is we want to know the difference between the two population means when we don't know the population standard deviation for both groups. As you all know, we often don't have access to the entire populations, or nor do we have access to the population means for both groups. But the good news is we can use the sample means for both groups as estimates of the population means. We compute the independent samples t-test when we have a between subjects design. So if you remember back to our conversation last week, we have a between subjects design when our groups are unrelated. And we have two groups. The independent variable is measured on a nominal scale, and the dependent variable is measured on an interval or a ratio scale. So now that we have the context for when we should compute the independent samples t-test, let's go through the steps of null hypothesis testing concerning this particular test. So as you all know, we start our null hypothesis testing by stating our statistical hypotheses. So first we start with the null hypothesis, and the null hypothesis essentially says there's no difference between the two population means. We can denote this by saying H0, and then we have mu for group 1 equals mu for group 2. The alternative hypotheses can look one of two ways. So the first way is we have a non-directional alternative hypothesis. In this situation, we're saying there is a difference between the two population means, but we don't know which group is higher than the other group or which group is lower than the other group. So we simply say mu for group 1 does not equal mu for group 2. We could also word our alternative hypotheses in a more specific way. So if we have directional alternative hypotheses, we could say that mu for group 1 is less than mu for group 2. One way to write this out as a sentence would be, on average, the scores from group 1 are lower than the scores for group 2. So I could say for this alternative hypothesis, mu1 is less than mu2. If the mean for group 1 is higher than the mean for group 2, we would write it this way. mu1 is greater than mu2. So, just to review, we have our statistical hypotheses where we're talking about the mu's for both of our groups. Next, we're going to identify our statistical test and level of significance. Remember, when it comes to step 2, here's where we should go through our two sample test decision tree. So remember, the first question is, how many samples do I have? For us, it's always going to be 2. Then we ask ourselves, do I know sigma 1 and sigma 2? In this situation, the answer is going to be no. So the next question that we ask ourselves is, do I have large samples? Remember, in this class, we're defining large samples as n being greater than or equal to 30. For us, we're saying we're going to use our independent samples t-test when both of our n's are less than 30. So now that we know which test we're doing, we also have to identify the level of significance. For this, we're going to use our same convention. If 0.05 is stated in the research scenario, then we're going to go with it. If it's another level of significance, then we'll go with that. If the level of significance is not stated in the research scenario, then we should assume that it's 0.05. From there, we're going to select the sample and collect some data. That's step 3. Now for step 4, we're going to find our regions of rejection. So if you all think back to our one sample t-test, and even for our correlated samples t-test, we needed to know alpha, we needed to know if we had a directional or non-directional alternative hypothesis, and we also needed degrees of freedom. Notice here that our formula for degrees of freedom has expanded because we have two groups. So here we're going to take N1, which is the sample size for group 1, subtract 1 from it, and then add that to N2 minus 1. Another way to write this is capital N minus 2. Now, up to this point, we've mainly been talking about our lowercase n's or our little n's, which represents each of the individual samples. But if we were to take the total number of participants in our sample, we would denote that as capital N. So that's why we're just doing capital N minus 2. And that's our formula for degrees of freedom for our independent samples t-test. Our next step is to calculate the test statistic. So notice that our test statistic looks a little bit different than some of the other formulas that we've seen before. We are going to start by subtracting our mean from group 1 from our mean for group 2 minus 0. Now, our null hypothesized value a lot of the times is 0, but sometimes it's not going to be 0. So tomorrow in class, I'll show you another way to write our numerator for our independent samples t-test. Sometimes you'll see people replace that 0 with mu1 minus mu2, which is the null hypothesized value. Since we're using the pooled variances t-test, we must first compute the pooled variances for both groups. And this is based on the notion that in the population, the variances for both groups are equal, which is one of the assumptions for the independent sample t-test that you should have read about in your textbook. If the variances are not equal, then we should use the separate variances t-test, which is on page 209, but there are some issues with this formula. We're not going to really get into the separate variances t-test formula in this class, but you can read about it in your textbook. So let's break this formula down a little bit more. So in our formula, we notice that we have this S squared P. So this S squared P stands for pooled variance. So in our denominator, we're going to take the pooled variance, divide that by N1, and then add that to the pooled variance, and then divide it by N2 again. And then take the square root of this entire thing. When we go through all of those phases, dividing our pooled variances by the sample size for both groups, and then taking the square root of that, we call that the standard error of the difference. Now, our standard error of the difference is the estimate of the standard deviation for the sampling distribution of the differences. So some of you are probably like, Dr. Major, what in the world is a sampling distribution of the difference? So remember back to our one sample test and our correlated samples t-test. In those tests, we took our observed sample value, which was our sample mean, and subtracted it from the null hypothesized value, and then we divided all of them by our standard error of the difference. And remember back to our sampling distribution of the difference conversation, our sampling distribution of the mean conversation, we said that our standard error of the difference are the values that fall along our x-axis. So essentially, it's our standard deviation for the sampling distribution of the mean. It tells us how far our sample mean is from the null hypothesized value in standard error units. So for our independent samples t-test, we have a new distribution. We call this distribution the sampling distribution of the differences between the means. So in the middle of this distribution, you'll see that the number is 0. This 0 stands for the fact that in our null hypothesis, we're saying there's no difference between the means for these two groups. But the reality is there may be a difference between these two means. So as that difference increases, then our x bar 1 minus x bar 2 is going to increase in a positive or negative way, depending on which group is larger than the other group. So with our pooled variances t-test formula, our denominator, our standard error of the difference, tells us how far our difference for our two means falls from the null hypothesized value, which a lot of times is going to be 0. So why do we need the pooled variance? If we go back to our formula for 1 second, why do we need this S squared P? Why can't we just take the standard deviation for both groups? Well, the reason is we have these two samples or two groups, and we have subsequent measures of variability for both groups. We have variances and standard deviations for both groups. The respective variances for each group may not be equal due to sampling error. Therefore, we have to take the average of the two. But if the sample size for one of the samples or for one of the groups is a little bit larger, then that's going to impact our pooled variance. So we weight the variances for both groups by including the degrees of freedom, which is n minus 1 for each sample. Our formula for pooled variance therefore looks like this. We take the sample size for group 1 and subtract 1 from it. Then we multiply it by the variance for group 1. We add that to the sample size for group 2 minus 1 times the variance for group 2. We take that whole thing and divide that by the sample size for group 1 plus the sample size for group 2 minus 2. From there, we can go back to our independent samples t-test formula because now we have everything that we need. We know our mean for group 1, we know our mean for group 2, and then we're going to take that and divide it by the pooled variance divided by n1 plus the pooled variance divided by n2, take the square root of all of that, and that's how we get our t value. Once we have computed our test statistic, we need to know if it falls in the region of rejection or not. If it does fall in the region of rejection, then we reject the null hypothesis. If it does not, we retain the null hypothesis. And then we do our interpretation. Our interpretation should include our test statistic, or specifically our t statistic, our degrees of freedom, and our p-value.